Archimedes' principle says any object wholly or partially immersed in a fluid would experience a buoyant force that equals to the weight of the displaced fluid. There is a story behind the Archimedes Principle. In the 3rd century BC, King Hero of the Second gave some gold to a goldsmith to make a crown. When the crown was done, the king suspected that the goldsmith had cheated and slipped some silver into the crown. So the king asked Archimedes to determine if the crown was made of pure gold. The legend was that the solution occurred to Archimedes when he was taking a bath. He jumped out of the bathtub, ran into the street naked, and shouted, "Eureka!" which means, "I found it." What did he find? Archimedes figured out a simple test that can tell him if the crown is made of pure gold. He could hand the crown and a block of gold of equal mass on a balance, so the two could balance like this in air. He can then lower both objects into water. He knew that silver was not as dense as gold, so silver of the same mass would occupy more volume than gold, displacing more water, and therefore would subject to higher buoyant force. If the crown has silver mixed in it, it would experience more buoyant force and the balance would tilt like this. Archimedes' test successfully proved that the crown was not made of pure gold, so the goldsmith got punished for his crime. Now let's look at the proof for Archimedes' principle. We can look at both objects wholly immersed or partially immersed in a fluid. For a fluid at rest, we know that the force from the fluid pressure ρgh is always perpendicular to the contact surface. So the force from fluid pressure would act on immersed objects like this. The deeper part experiences higher pressure than the shallower part. So the net force from fluid pressure on the object would go upward, and that is the buoyant force. So there's the buoyant force over here too. Now I will remove this object and fill this space with a pack of fluid that is exactly the same shape and size as the object. If this pack of fluid is identical to the fluid in this container, this pack of fluid should be able to stay at rest in place. Since the surrounding fluid is exactly the same as before, the surrounding fluid should provide this pack of fluid with exactly the same buoyant force as before. Since this pack of fluid can stay at rest, the net force on it must be zero. Therefore, the buoyant force must cancel with its mg exactly. And this leads to the buoyant force being equal to the weight of this pack of fluid, which is exactly the same as the weight of the fluid displaced by this original object, which means the buoyant force experienced by this immersed object must equal to the weight of the displaced fluid. The same also works for an object partially immersed in a fluid. This object displaces this much fluid, and for this pack of fluid, the mg is equal to and is balanced by the buoyant force. Same amount of buoyant force as that. So the buoyant force would equal to the mg of the displaced fluid. If you prefer more mathematical proof, we can use this simplified proof. Here, I have a rectangular block submerged in a fluid with density ρ. The force from fluid pressure is perpendicular to the contact surface, and the deeper, the larger the pressure. Because of symmetry, we can see that the force from the two sides, they cancel completely. But the force from the top and the bottom here, they do not cancel. So we need to find the force pushing down on the block and the force pushing up on the block. Let's say the top surface is at a depth h1. The bottom surface is at a depth of h2. So the upward force pushing up on the block would equal to the pressure times the area. The pressure down here is the atmospheric pressure PO plus the rho g H2. So this is PO plus rho g H2 times the cross-sectional area A of the block. The force going down on the block is also pressure times the area. The pressure up here is PO plus the rho g H1 times the area. And we know that the upward force is bigger than the downward force. So if I subtract the downward force from the upward force, I would get the net buoyant force from the fluid. That is, this minus that, the PO terms would cancel, and I can factor out the rho GA. So it's rho GA times the H2 minus H1. And the cross-sectional area times the H2 minus H1, which is the height of the rectangular block. That means area times the height. That gives us the volume of the block. And the density times volume is the mass. So this gives us the mass times the G. And this is the density of the fluid. So this M is not the mass of the block, but the mass of the displaced fluid, because this is the fluid density times the volume displaced, which means the buoyant force equals to the weight of the displaced fluid. And that's the Archimedes principle.